Welcome everybody. This video is for the American Association of Physics Teachers virtual summer meeting in July 2020. In the video, I'll be summarizing teaching materials that I've developed for understanding COVID-19 by modeling it. Now, if you're a student, you might not want to watch this video before you actually look at the materials because there's going to be a lot of spoilers. The teaching materials are designed as a guided inquiry exercise, and so if you don't want to know what you'll be figuring out, I suggest you come back and watch this video later. Otherwise, if you're an instructor and want to know what the materials actually can do, this video's just for you. Okay, so let's start by talking about where you can find the materials. They're on the web at circle4.com/biophysics. This is the home page, and if you click on the sample chapters link, it'll take you to the sample chapters for a book that I'm working on with Cambridge University Press. Chapters 1, 2, and 3 are here at the top. The main topic for the video is going to be chapter 12, but before I do that, let's talk about chapter 1. Okay, so here's the cover page for chapter 1. One of the things I'd like you to pay attention to is this finite difference diagram on the cover. It's one of the main features of the book, and we'll get to that when we get to chapter 3. Now, the main reason I wanted to talk about chapter 1 was just to tell you what it's about, because it's kind of preliminary stuff that the students will find useful. The main topic for the chapter is the marble game, which is a Monte Carlo simulation of diffusion, and marbles jump from one box to another using a random choice, and that simulates diffusion. The other main purpose of the chapter is to introduce how to use Excel to do quantitative modeling. The chapter starts right at the very beginning with telling students how to enter things into cells, how the cells work, how formulas work, and it moves on from there. Chapter 2 is primarily about introducing students to the idea of writing an algorithm. And so here's a handwritten algorithm. It has various features. The parameters column here are the constants for the simulation. Then we have variables, which become columns in the spreadsheet. Step 0 is setting up the simulation, and step 1 is the main part of the algorithm that's repeated in each row of the spreadsheet. One of the things that I make a big deal about is getting students to do unit checks, because in biophysics and life sciences in general, it's common that the units are not standard SI units, and so they always need to pay attention to those when they're doing quantitative modeling. Chapter 3 is primarily an introduction to using finite difference methods. Here's a diagram that describes how the finite difference methods work. So if students aren't familiar with that approach, then you should work through parts of chapter 3. So here's chapter 12. It's the thing that we're going to spend most of our time talking about. After some introductory comments, we start out with probably the simplest possible model of epidemiology, which is what I call an unlimited growth model. And the way it works is that you've got the population split into two groups: susceptible people and people who are infectious. Those are the only two choices. The arrow here indicates that people can go from being susceptible to being infectious, going from box S to box I. The arrow is labeled with this expression. Ki is the infection rate constant, and Ni is the number in box I. In question 1, we go over how to write an algorithm, and there's a separate YouTube video about how to do that if students have trouble. They start out by downloading a pre-formatted spreadsheet, and with that spreadsheet they're able to generate a finite difference model of the unlimited growth model, and then eventually compare it with USA data. So here on the y-axis we have the new infection rate, RI, and that's given as confirmed cases per day, and on the x-axis we have time in days. And as you can see, the unlimited growth model actually does a pretty good job for the first 19 days or so. Section 2 of the chapter introduces a new model, the finite population model. It has the same two boxes, and the only difference now is that the infection rate includes this term lowercase s, which is the fraction susceptible. It's the number susceptible divided by the population size. Changing to that model makes the model much, well, more realistic, and it actually allows us to talk about the idea of flattening the curve by social distancing in this finite population model. Section 3 introduces the SIR model, and it's the same as the previous models except that we've now added a third box for people who can recover. And so now there's a recovery rate constant, and it's multiplied by the number infectious, and that gives the rate at which people recover. The SIR model is both the origin of the basic reproduction number R0, which tells you how frequently people infect others, and the concept of herd immunity. The SIR model, when you fit it to the first 19 days, predicts a rather alarming exponential growth that eventually tops out at about 2 million infections per day. And I call this the Exponential Dragon. This Exponential Dragon, when you look at it on a linear scale of the infection rate versus time, shows a very large peak, and on a semi-log graph it has a rather characteristic inverted V shape, which we'll talk more about later. Another feature of the SIR model is that it can show extreme sensitivity to initial conditions, and this graph shows what happens if we adjust the fitted data by just 1 day at a time, and it produces this series of 4 graphs that show quite a dramatic change in qualitative behavior. There's also an exercise where students fit the data to just the first 2 weeks of April and show that it successfully predicts what happens all the way through to Memorial Day. There's also an exercise for students to estimate how many lives could have been saved if social distancing had been implemented just 7 days earlier. There's also an exercise which could obviously be adjusted as time goes by for predicting how many infections occur and how many deaths. Section 6 introduces a method to model the transition from exponential growth to the period of social distancing. And using that model, with the assumption that the whole of America behaved like New York City, students can predict how many lives could have been saved if everybody had done it New York's way. Using the same matching techniques, students can also model what's happening now at the beginning of July, and you'll see that there's another exponential dragon approaching. And if it's plotted on a longer term scale, we'll see that the prediction can be that there'll be hundreds of thousands of people infected per day. And again, the graph shows the characteristic inverted V shape for the exponential dragon. So in conclusion, there are many activities that the students can do based on these materials, which you can find at circle4.com/biophysics, and look at the top of the page for the link to the free chapters and the videos.